Okay, so the idea now is to talk about the connection, or why a square matrix that preserves the inner product must be orthogonal in the real space or unitary in the complex space. So let's start. If I say that a square matrix preserves the inner product, it specifically means this one. This means that for every two vectors x and y, when I apply A and I take the inner product, I get the same value as if I just take the inner product between the two vectors for any two vectors. Okay, so from this preserving of the inner product, we want to conclude that A is unitary if we're talking about the complex space, and it is the definition is A complex conjugate A equals I, or orthogonal in the real space. That means that A transpose A equals I. That's what we want to show. So we start with preserving the inner product, as we said, this one. And you can write this by the definition of inner product like this in the complex space or this in the real space. Okay, and on the right side you can write it on this in the complex space or this in the real space. We continue. Now this one you can write it as this. Look, you take the a from here and a from here, and you take the complex conjugate from here, so you just transform the position of x and a, and you get this one, and this equals what was in the right side, which is this one. Okay, for the real space, the same idea, just with the transpose. Now, in order for this to hold for any x and y, it means that x complex conjugate and y just equal itself without this. It means that what sits here, if this holds for every x and y, it must be something that does not change x and y, the multiplication between them. But the only matrix that do that for every x and y is the identity matrix. The same thing goes for the real case. So we just conclude that A complex conjugate A equals I in the complex case, or A transpose A equals I for the real case. In the complex, we call it a unitary. In the real, we're talking about an orthogonal, and this is the definition for a unitary and an orthogonal matrix. So we saw how we just started with preserving the inner product, got to this equation for every x and y, and concluded that it must hold that A complex conjugate A equals I, or A transpose A equals I, which is definition for unitary and orthogonal respectively, and that's it.